students, I welcome you all for another lecture on the course Microprocessors and Microcontrollers. In today's class, I am going to discuss about a concept timers in PIC 16 F877 microcontroller. This particular microcontroller PIC 16 F877 have three timers. Those are timer 0, timer 1 and timer 2 along with watchdog timer WT. So I repeat my point. This particular microcontroller has three timer circuits: timer 0, timer 1, timer 2 along with watchdog timer WT. These timers, what actually they are doing is, these are counting the input clock pulses. The important thing is, these clock pulses are getting from either internal oscillator circuit or from external world. That is an important. If they are getting a clock signals from internal oscillator circuit, then your circuits act as a timers. Whenever they are getting a clock signals from an external world, that time they are acting as counters. That we know that. So now I am going to discuss these timers one by one. Straight away. I start my discussion with timer 0. This timer 0 is 8-bit timer / counter. I simply written as it is an 8-bit timer, but it is 8-bit timer / counter circuit. That means it is act as a timer as well as it is act as counter. The size of it one is just only 8-bit, so that it will count the number of clock pulses are 2 power 8. That is equal to 256 clock pulses. My second point is, it has a programmable pre-scaling option like our PIC 16C61/71. That means in order to increase the number of clock pulses counted by my timer without increasing its size, then what I have to do is, I took the help of this pre-scaling option. Originally my 8-bit timer can count only 256 clock pulses. To count the 256 clock pulses, it will take 250 seconds. Like you can assume, to count a single clock pulse, it will take 1 second. That means by using this 8-bit timer, I can go and provide maximum delay of 256 seconds. But for different applications, I want more than that time delay. That means I need more than 256 seconds with the same timer 0. Without using this pre-scaling option, I was unable to get it without increasing the size also. So here I was using pre-scaling option. By using that, I can go and produce much more delay without increasing the size of a timer. So that is an important. And next, the clock input for this timer can be either internal or external. That means the timer 0 get a clock signal either from an internal oscillator circuit or it can receive the clock signal from external. Once it receives a clock signal from an internal oscillator circuit, then your timer 0 is act as a timer itself. Whenever it receives a clock signal from an external world, the time your timer 0 is act as counter. You remember that. And coming to the next point, an interrupt is generated after it overflows from 0FFH to 00H. That means this timer 0 generates overflow interrupt. Whenever the count value present in this timer 0 rolls off its value from maximum to minimum. That means whenever the content of your timer 0 rolls off its value from FFH to 00H, why? Because FFH is a maximum value. That means the 8-bit timer has 8 ones. Once it receives a new clock pulse, what happens is its content is changes to 8 zeros. 8 zeros is equivalent to 00H. That was a minimum value. So your timer 0 may generate an overflow interrupt whenever its content is rolls off from maximum to minimum, that is FFH2 00H. That we have to remember. And coming to the next one, that is timer 1. Your timer 1 is a 16-bit timer / counter, no doubt. In previous cases, it is just only 8-bit timer / counter, but now timer 1 is a 16-bit timer / counter. No doubt, it is act as a timer when it receives the clock signal from internal oscillator circuit, or it will receive the clock signal from an external load. Then the same timer 1 is act as a counter itself. This timer can be formed by the combination of two 8-bit registers. Number one is a TMR1H and another one is a TMR1L. This is a TMR1, that is nothing but a timer 1, and here H represents higher byte. It is a higher byte, and this L represents a lower byte. Lower byte. That means, let you can assume, friends, this is my timer 1. This is my timer 1. It is a total 16-bit. It can be formed by the combination of two 8-bit registers. Let you can assume this is the first 0 to 7 and this is the next 8 to 50. This 0 to 7 is nothing but our TMR1L, because timer 1 lower byte, and from 8 to 15 forming as a higher order byte, which is a TMR1H. Like this, your timer 1 can be formed. So that's the meaning of that. So an interrupt can be generated after its content rolls off from 4SH to 40H. Again, the case is same as previous timer 1. So timer 0. This timer 1 also generates overflow interrupt whenever the content of this timer 1 rolls off its value from maximum to minimum. That time this timer 1 also generates an interrupt. Here what's the maximum value? 16 ones. 16 ones equal to X value is 4Fs. What's the minimum value? 16 zeros. What's equal to X value? That is 4 zeros. Whenever the timer 1 content rolls off or changes its value from 16 ones to 16 zeros, then this timer 1 generates overflow interrupt. That's the meaning of that. The interrupt flag of timer 1 is TMR1IF. TMR1IF. What's the timer overflow flag of a timer 0? That was a T0IF. T0IF. That is present in INTC world. But now this TMR1IF is present in PIE1 register. That means peripheral interrupt enable register 1. The timer 1 related overflow flag was a TMR1IF, which is present in PIE1 register, but the PIE1 is peripheral interrupt enable register 1. So that's the meaning of this. This interrupt can be enabled by using a TMR1IE bit in PIE1 register. So here important one is we can enable or disable this timer 1 overflow interrupt with the help of a bit called TMR1IE, which is present in PIE1 register. Sorry friends, this flag is originally present in PIR1, peripheral interrupt request register 1. So TMR-IE was present in PIE1, peripheral interrupt enable register. So this is timer 1 related information. So coming to T1C1, that is nothing but timer 1 control register, is a register associated with the timer 1 operation. So we have a control register is there in association with the timer 1, which is called a T1C1. The timer clock can be either internal or an external. It is decided by a bit TMR1CS. That means timer 1 clock select. Timer 1 clock select. This is a bit that was present in T1C1 timer 1 control register. By using that bit, I decide my clock signal is from an internal oscillator circuit or from an external load. Based on that only, I can decide my timer 1 is act as a timer or it is act as a counter. And another one is This timer also have a pre-scaling option. This timer also having a pre-scaling option, because like in the previous case, the maximum number of clock pulses that can be counted by our timer 1 is 2 power 16. That means 65,536 clock pulses it will count. In order to need much more time delay, more than 65,536 clock pulses duration, I definitely took the help of a pre-scaling option, like our timer 0 case. Your timer 1 have a pre-scaling option. That also we do by using T1 CON register bits, that is T1 CK PS1. That means timer 1 clock pre-scaling bit 1 as well as T1 CK PS0. There are 2 bits. Timer 1 clock pre-scaling bit 1 as well as timer 1 clock pre-scaling bit 0. By using these 2 bits, we can select a pre-scaling option for timer 1. Next, timer 1 can be started or stopped by using a bit called TMR1 on. Again, it is present in T1 CON register. That means in order to start or stop counting of a clock pulses by your timer 1, with the help of a bit called TMR1 on bit, if the bit is set to 1, your timer 1 start counting of input clock pulses. If the bit is equal to 0, your timer 1 stop the counting of input clock pulses. This bit also present in a T1 CON register. And next, oscillator can be enabled or disabled using T1 OSC EN. T1 represents timer 1, OSC represents oscillator, and EN represents enable. Timer 1 have its own dedicated oscillator circuit for generation of clock pulses. Whenever timer 1 is act as a timer itself, we can enable it or disable it with the help of this particular bit. This bit also present in our timer 1 control register T1 CON. Next, timer 1 can operate either in a timer or counter. That already I told you. The clock select bit, that is a TMR1 CS bit in T1 CON, determines timer operation or counter operation. Already I told you, TMR1 timer 1 CS means clock select. So based on the clock selection, it is act as a timer or it is act as counter. Next, TMR1 CS is equal to 0, this bit is equal to 0, then it will select the internal clock. The time your circuit is act as timer itself. And already told this point also. Whenever a timer circuit get a clock signal from an internal oscillator circuit, that time your circuit is act as a timer itself. Whenever it will accept the clock signal from an external world, the time your circuit is act as event counter. That we programmed here with the help of a bit called TMR1 CS, which is a part of our T1 CON register. That you remember, friends. In timer mode, T1's S, Y, and Z. That means timer 1 sync bit has no effect because internal clock is selected. So here important thing is we have to go to synchronize the clock pulses when we are receiving from an external world with respect to the internal operation of your timer. Whenever your circuit is act as a timer, no need of synchronization. That's why this T1 synchronization bit is no effect because we are receiving a clock signal from an internal oscillator circuit. And next, whenever it is counter mode, this T1 sync is clear, then the external clock input is synchronized with internal clock. Whenever this bit is set to 0, it was a clear, then externally received clock signal is synchronized with the internal clock. That means there is a synchronization between an external received clock and internal clock. So see here guys, this is T1 CON register format. So that is TMR1. By using this bit, we can turn on or turn off our timer 1 operation. By using TMR1 CS, that means you have select clock for timer 1. That means with the help of this bit, we can select our timer is act as a timer itself or it is act as a counter. And T1 SY and C, this is a timer 1 sync bit. This is especially useful for us when we are accessing a clock signal from an external world to synchronize it with the internal clock or not. And next T1 OSC EN, this is a bit which is used to enable or disable timer 1 oscillator, and next are T1 CKPS0 and T1 CKPS1. These are two are timer 1 clock pre-scaling bits. This is a pre-scaling factor. If both are set to 0 0, one clock pulse is equal to increment the content of 1 by your counter, and if it is set to 0 1, that means the content of timer 1 is incremented by 1 by receiving of 2 successive clock pulses. If it is 1 0, by receiving of 4 clock pulses, then and only your timer content is incremented by 1. If these two are 1 1, by receiving of 8 successive clock pulses, then and only the content of timer 1 is incremented by 1. So that is this particular register T1 COM. And coming to the third timer is timer 2. So this is an 8-bit timer with pre-scaling and post-scaling. This is very important, friends, because if you go for timer 0 or a timer 1, they have only pre-scaling option, but coming to timer 2, it has both a pre-scaling as well as post-scaling option. Both are programmable. That means user can select a pre-scaling value as well as a post-scaling value by programming of particular bits of pre-scaling as well as post-scaling bits which are present in timer 2 control register. That we can go and see. Selection of pre-scaling and post-scaling was done timer 2 COM register. Yes, pre-scaling we can do it as well as post-scaling we can do it. See here, guys, this is your timer 2 register. So every time timer 2 has a register called period register 2. These are two values are compared by your comparator. So whenever we got an equality case, that is after post scale. So after post scaling, it will set a timer 2 overflow interrupt. That is a timer 2 IF. It will set it. And whenever we got equality condition, how many number of times you got an equality, the times you can go for this post scaling. And one more thing is PMR2 register. We are not using this PMR2. That time your timer 2 may generate some output whenever we are getting equality cases, because this timer 2 was participating in our capture / compare / PW module operations. Whenever we are doing a capturing option, the time this timer 2 value we can retrieve from this. Whenever we are doing a comparison case, then this timer 2 value is comparing with the period register value by a comparator. Whenever we got an equality, that is a post scale, and automatic timer oscillator can be generated. So see here, guys, it is a pre-scaling factor is that we do with the help of pre-scaling bits. Those are present in our T2 CON register. This is a post scaler. They may have 4 bits. By using that, I can go and select different post scalings for timer 2 operation. And here important thing is, if oscillated by 4, it is received by the pre-scaler. That means every machine cycle have 4 complete clock cycles present in this PIC 16F877 control. That's the meaning of this. That means whatever the oscillation frequency that will be generated by internal oscillator, that is a passes through divided by 4 before reaching this pre-scaler circuit, because every machine cycle have 4 complete clock cycles. That's why here always the received clock signal is F oscillator divided by 4 itself. You have to remember that. So timer 2 has an 8-bit period register. Just now we can go through that. Timer 2 increments from 00H until matches PR value, and after that resets it to 00H during the next increment. Whenever period register value is matching with our timer 2 value, then automatically your timer value is resets. That means again it is go for a 00H. That's the meaning of that. Upon resets, PR2 is initialized to FFH. So again it is initializing with FFH. That means the maximum value I can store down to PR2. Again that value is frequently comparing with the timer 2 value. Again your timer 2 start counting of clock pulses by receiving from pre-scaler circuit one after other. And next, the match output of our timer 2 again has a post scaler. So whenever we can got equality case, the information we are giving to post scaler, so that we can go through the previous diagram. Any match generates an interrupt timer 2 IF is generated, which is present in PIR1 register. So TMR2IF means a timer 2 interrupt. Whenever a period register value is matching with our timer 2 value, then this circuit may generate this particular interrupt by your oscillar circuit. So that particular bit is present in PIR1 register. PIR1 is a peripheral interrupt request register 1, and oscillar counts the number of times period register value is matches with the timer 2. So timer 2 register is one of the input for your comparator, and another input for your comparator is a PIR2 register value. Once both are matches, then it will produces equality condition. So that is this. So see here friends, that is timer 2 control register format. So this is a TOUT PS3, TOUT PS2, TOUT PS1 and TOUT PS0. These are 4 auto oscillar bits, and timer 2 turn on or turn off, that we do with the help of timer 2 on bit. And this timer 2 have a pre-scaling bits, that is a T2 CKPS1 and T2 CKPS0. Sorry, it is not 1 guys, it is 0, sorry. So by using those 2 bits, I can go and select a pre-scaling. See here friends, T2 CKPS1 and T2 CKPS0, I have a 3 pre-scaling factors. If both are 0, 0, 1 clock pulse is equivalent to 1 count value. So 0, 1, by receiving a 4 clock pulses, your count value is increment by 1. If it is 1 don't care, that means 1, 0 or 1, 1. By successful receiving of a 16 clock pulses, the content of your timer 2 can be increment by 1. So like this, we can do a pre-scaling selection with the help of least 2 significant bits of this. In a similar way, we can do post-scalar selection by using these 4 bits of our timer 2 control register. See here friends, that's the structure. So if 4 bits are 0, 0, post-scalar is 1:1. So 0001, 1:2, 0010, 1:3. So 0011, 1:4, and 4 once it is 1:16. That means you are getting 16 times equality condition. 16 times equality condition between our timer 2 value and our period register value. So then it is equivalent to consider as 1. So that is this post scaling. So that is about timers concept. That is about a timers concept in PIC 16F877. So I hope you understand the timers operation in PIC 16F877. In the next class, I am going to discuss about interrupts in PIC 16F877. Thank you for patient listening.